Quantum computing is set to revolutionize technology, promising to solve problems that are impossible for even the fastest supercomputers today. But to unlock this potential, it needs a special ingredient: quantum light, which is far more complex than the light we use every day. Unlike the light from a bulb or a laser pointer, quantum light is made of entangled photons, tiny particles of light that are mysteriously linked, no matter how far apart they are. This entanglement is what powers the unique abilities of quantum computers. Creating this special kind of light isn't easy. For years, scientists have relied on massive, delicate lab setups filled with mirrors, lasers, and sensitive equipment just to produce a few entangled photons at a time. These setups are not only expensive and fragile, but also far too large and impractical for real-world applications outside the lab. To make quantum computers truly useful, we need a source of entangled photons that is compact, stable, and can be manufactured at scale, something that can fit inside a device, not just a laboratory. Think about how early computers filled entire rooms, but now, powerful chips fit in your pocket. Quantum technology needs a similar leap in miniaturization and practicality. That's why a breakthrough from Boston University is so exciting. Researchers there have created a chip that generates quantum light on a single, tiny platform. No bulky lab required. This isn't just about shrinking things down. It's a self-contained system that can reliably create and manage quantum light, all on a chip smaller than a coin. The chip brings together three cutting-edge fields: electronics, photonics, and quantum technology, into one powerful device, opening the door to new possibilities. This innovation could finally make quantum computers practical, powerful, and ready to tackle real-world challenges, from cryptography to drug discovery. The future of computing may just fit on the tip of your finger, ushering in a new era of technology that once seemed impossible. What makes the Boston University chip truly special? And why is it generating so much excitement in the world of technology? It's a hybrid marvel, seamlessly combining electronics, photonics, and quantum technology, all on a single silicon platform, something that was once thought to be nearly impossible. Traditionally, these systems were bulky, fragile, and expensive, with separate parts wired together, often filling entire rooms and requiring constant maintenance. By integrating everything onto a single chip, the technology becomes far more robust, energy efficient, and ready for mass production at a scale never seen before in quantum devices. It uses the same advanced 45-nanometer CMOS process as today's most powerful computer chips, making it both scalable and affordable for widespread use. This means quantum chips could soon be manufactured in the same high-tech factories as the electronics we rely on every day, accelerating their adoption. Integration allows for instant, high-speed communication between components, which is absolutely crucial for controlling delicate quantum states and ensuring reliable operation. The chip can monitor and adjust itself in real time, using built-in diagnostics to ensure stable quantum light production and optimal performance. It's not just a component, it's a complete quantum light factory on a chip, capable of generating, manipulating, and controlling quantum signals. This breakthrough paves the way for building complex, scalable quantum circuits that could revolutionize computing, communications, and more. The leap from isolated lab experiments to real-world quantum technology is finally within reach, opening doors to innovations we can only begin to imagine. The era of practical, accessible quantum devices has truly begun, marking a new chapter in technological progress. At the heart of the chip lies the Microring Resonator, a microscopic racetrack for light, crafted with incredible precision on a silicon wafer. These tiny rings are engineered to guide and trap light, allowing it to circulate in a loop, much like cars speeding around a track. When laser light enters the ring, it travels around and around, circulating and intensifying with each pass. This unique structure amplifies the light's interaction with the material, making the microring a powerful tool for manipulating photons. This resonance creates the perfect conditions for generating quantum light, a special kind of light with properties that classical light simply doesn't have. When the laser's frequency matches the natural frequency of the ring, energy builds up dramatically, enabling a process called spontaneous four-wave mixing, a key quantum effect. In this process, two photons from the laser interact inside the ring, creating two new photons that are entangled, meaning their properties are linked, no matter how far apart they travel. These entangled photon pairs are the essential building blocks for quantum computing and ultra-secure quantum communication, opening doors to new possibilities in information technology. Microring resonators are incredibly tiny and efficient. Thousands can be integrated onto a single chip, making large-scale quantum devices possible. This scalability allows for the mass production of entangled photons, which is essential for building powerful quantum computers and networks. The microring is truly the engine that transforms ordinary laser light into quantum light, driving the next generation of photonic technology. Manipulating light at this microscopic scale is unlocking revolutionary new technologies, from quantum encryption to advanced sensors. The future of quantum information and communication truly starts with these tiny yet powerful microring resonators. Creating entangled photons is just the start. The process is delicate and easily disrupted. The chip uses on-chip photodiodes and heaters to monitor and adjust itself. Photodiodes act as sensors, measuring the light from the microring in real time. If the light drops, it means the system is out of tune. Tiny heaters built into the chip make precise temperature adjustments to retune the microring. This keeps the resonator perfectly aligned with the laser, ensuring steady photon production. The chip constantly measures and corrects itself, all automatically. This self-regulation is key to reliable quantum light generation. Stability and precision are built right into the chip. The chip's control electronics are its brain, coordinating the sensors and heaters. All circuits are integrated on the same chip, enabling instant feedback and adjustment. When photodiodes detect a problem, the electronics analyze the signal and send precise commands to the heaters. Even tiny temperature changes can make a big difference, so precision is critical. Having the brain on chip means the system responds in real time. No delays, no external computers. This makes the chip robust against disturbances and keeps quantum light production stable. Smart integration is what makes this chip truly autonomous. The chip operates through a rapid feedback loop, like a thermostat but at the quantum level. Laser light enters the microring, producing entangled photons. Photodiodes measure the output, sending signals to the control electronics. If the light isn't perfect, the electronics calculate and send corrections to the heaters. The heaters adjust the microring's temperature, bringing it back into alignment. This cycle repeats thousands of times per second, keeping the system stable. The chip actively resists disturbances, maintaining a steady stream of entangled photons. Without this feedback, quantum systems would quickly fall out of tune. With it, the chip delivers reliable quantum light for real-world applications. This integrated chip marks a turning point for quantum technology. It solves the challenge of creating stable, scalable quantum light sources. The impact goes beyond computing. Entangled photons enable ultra-secure quantum communication. The chip could power unhackable networks and accelerate quantum research worldwide. Scientists can now focus on new quantum applications, not just building complex setups. Like the integrated circuit revolutionized classical computing, this chip could do the same for quantum tech. The impossible is becoming practical, one tiny chip at a time. The quantum future is here, and it's brighter than ever.